Welcome to another episode of NASA Science Live, an opportunity for you to interact with NASA experts and have your questions answered in real time. I'm your host, Tahira Allen, and today we're joining you live from NASA's Goddard Space Flight Center in Greenbelt, Maryland. 1 year ago today, the James Webb Space Telescope released its first full-color images and data and had us all in awe at the beauty of the universe. As the world's most powerful infrared space telescope, Webb has been examining every phase of cosmic history, from the first luminous glows of galaxies in the early universe to the evolution of galaxies, as well as stars, planets, and objects in our own solar system. Today, we're going to highlight some of Webb's exciting discoveries over the past year, get a look at what's next for this historic mission, and answer your questions throughout the show. Send in your questions using the hashtag AskNASA on social media or drop them directly into the comment box wherever you're watching. I'm joined today by two astronomers who are going to guide us through Webb's first year in science. Dr. Jane Rigby, who is the Webb Senior Project Scientist at NASA Goddard, as well as Dr. Macarena Garcia Marin, who is a Webb Deputy Project Scientist at the Space Telescope Science Institute and a member of the European Space Agency. Thank you both so much for being here with us on such a big day. So if you could just start by telling us a little bit about your roles on the mission and then how you're feeling today.
By all means, so thank you so much for having us. I've been part of the mission for about 16 years, and throughout those years I have had different roles. Right now I'm the Deputy Project Scientist for Space Telescope and Science Institute, and that means that I interact with the community, I oversee that things are working as expected, and really try to give them what they need to publish great science. How I feel today, it's incredibly happy for this accomplishment. The first year has been fantastic, really. And this is a testament to everybody who worked on the mission. So we have 3 agencies, NASA, ESA, the Canadian Space Agency, 13 countries, and 20,000 people to make this happen. So it's really, it is amazing. Amazing, yeah, for one telescope.
Oh, wow, and what about you, Jane?
Sure, so as the Senior Project Scientist, my job is to optimize the science that we do with this amazing telescope, to make sure that we are doing the best science and giving the community what we need to really make these transformative discoveries, and then to make sure we're explaining those and sharing them with the world. How I'm feeling today is so proud of the team. People have poured their hearts and their souls into this mission, and we also are, it's so gratifying to see how many people around the world are with us on that journey. It's been such a wonderful year, and I know that we really are just getting started in terms of the scientific return from this telescope.
I mean, we have so much to get into today,
Yeah,
and we are just
let's go.
so honored to have you all. So over the past year, Webb has provided new understandings of how stars and their accompanying planets form. Just this morning, a brand new image was released in celebration of 1 year of Webb science operations. It shows us a detailed view of the closest star-forming region to Earth, the Rho-Ophiuchi cloud complex. Maka, this image just practically begs for an explanation. Could you start by just telling us exactly what are we seeing here?
By all means, and I always like to take a second to really take in the image, because it is really astonishingly beautiful. It has a structure, it has this organic feeling to it. It's really amazing. And yes, it is Rho-Ophiuchi, which is the closest star-forming region to us. And in this case, we're looking at a region with about 50 stars. For the most part, they are very similar to the sun. They are in terms of mass. And they are essentially in formation. They're just baby stars.
So nursery.
It is like a nursery of stars, and even though it is beautiful and has all these structures and there's a lot of activity going on, it is actually quite a relaxed for a star-forming region. So Jay, why don't you walk us through some of the details?
Sure. There's a lot to see. Let's go on a little tour.
A little tour. Let's do it.
Let's do it. All right. Okay. So as we're looking at the star-forming region, one of the first things that catches your eye is this sort of glowing mane down in the bottom, this sort of yellow lion's mane thing. What that is a massive star, is a little bit more massive than the sun, that has gotten out of its birth cloud. We also have regions that are still, where the stars are still in their birth cloud. They haven't gotten out yet. And we can see their glow of their disks as they're accreting matter onto the star. It takes a while for stars to form. They form out of a disk of gas and dust. And it's just gravity, right? It's just gravity accreting, and then there's more gravity, so then more stuff gets in. And then once those stars get enough mass to start shining, they can push back at the clouds where they formed. And so you can get like that beautiful ghostly lit up structure where it's actually that star lighting up its birth cloud. We also have, the colors here are really important. That yellow is dust that's been lit up. That red is molecular hydrogen. It's hydrogen that is coming from jets being spat out in these little these little two jets getting shot out of each of these new stars. And so all together we have, it really is like a nursery where the youngest stars haven't really gotten born yet, but they're far along. And then, right, they're along the path. And then the older ones are out, they're shining, and they're having an impact on the region where they were born.
Well, I mean, we've talked a little bit about stellar birth right now, right? So
Yes.
let's skip to the end of the movie. Like what happens at the end of a life cycle for a star like our sun?
So everything in a star depends on the mass, like the life and the number of years that it will be, it depends on the mass. And in the case of a star like the sun, so not too massive, what it will happen is that when it's nearing the end of its life, it will start shedding the outer shells and creating these beautiful structures around it, which are called planetary nebula. And they get lit up, and they are really, the level of detail with Webb on these structures is really fantastic. It really allows to study a lot of the fine detail of the planetary nebula. And so by the end of it, the star will slowly sort of switch off. It will become a white dwarf and then slowly switch off and just disappear. And then we have other type of stars that are slightly more massive, let's say about like 30 solar masses. And some of them are called Wolf-Rayet. And with Webb, we have studied some beautiful cases of Wolf-Rayet stars that are have like a companion rotating around it, and in that rotation, it actually creates these beautiful shells around it. So there's this case where you have a Wolf-Rayet star, 30 solar masses, the companion, and when they get close, the star sheds, because of the gravitational pull, shells of dust. Every 8 years, one. It's like a tree trunk of
so you
information.
can measure
It's
the
clockwork.
time.
Wow. You can measure the time because it's related with the way the stars rotate around each other. So it's truly amazing. And again, with Webb, you can study all the fine details and really see many of these rings that have never seen before in this level of detail and quality. It's amazing.
Wow.
And these stars will end up like a supernova, and then we have the very massive ones. And what happens after a supernova?
Sure. So with Webb, we have been studying stars that are close to dying, like that Wolf-Rayet star that's spitting out those dust clouds. And then we've also been studying stars that are dead, that have already exploded. So massive stars that have exploded as supernovae, and in their dying, they light up and blow up one of the brightest explosions in the universe and cast out these fast-moving clouds of dust and gas that have in them all of the elements that get formed when a star dies. It really is true. Carl Sagan used to say that we're all made of star stuff. That is literally true. The carbon, oxygen, nitrogen, iron in our bodies, we're all made in stars. Many of those elements are made in stars when they blow up. And so by studying supernovae and their remnants, the gas clouds that are left behind, we can understand how the stuff we're made of got formed in the hearts of stars.
And I mean, Webb just does such a beautiful job at peering through this dusk and like showing us things we haven't seen before. So this has been really, really phenomenal. Not only just like visually, but for the science, this is incredible.
Yeah.
And so many stars have planets orbiting around them. The ones outside our solar system are called exoplanets. Maka, how is Webb studying exoplanets?
So it mainly uses two techniques. One of them is direct imaging, taking a picture of the planet. And to do that, you first have to block the star, like you do with your thumb in the sun.
Close one eye.
Block the star, close one eye, and then you get the beautiful image of the planet next to it. And Webb has demonstrated this can be done beautifully, and we are getting data with this technique. And then the other technique is what we call a planetary transit. So essentially when a planet works its way in the orbit in front of the star. So we can measure the star before the planet goes in front of it and when the planet goes in front of it. It's like an eclipse. So in that process, the light of the star gets filtered by the planet atmosphere, and then we can measure the atmospheric composition of that planet thanks to that process of light filtering through it. With Webb, the level of high quality data we're getting with this technique and stability and really wealth of information, it's out of the chart. It really is.
Well, Jane, can you expand a little bit on what we are learning from these techniques, say with massive planets?
Sure, and now we're currently spending a quarter of all the observing time with Webb studying exoplanets. We ask for the world's best ideas, and then we pick the best. So we can respond to what good ideas people are having. But right now, people are having a lot of ideas for studying exoplanets. So some of the discoveries so far, and again, so for exoplanets, this was the big uncertainty for us. Webb wasn't built to do exoplanets. It was originally designed to study the most distant galaxies. We kind of added that science case in kind of late in the game.
Slid that in.
And it was a little, well, we'll see what we get, right? It turns out the telescope has been so stable. It has been gorgeous for exoplanets. And so the data that we're getting, in which we're looking at what the atmospheres around, what's inside these atmospheres of these planets orbiting other stars. And so the first data we got on those exoplanets, it basically just jumped out at us. We're like, oh, that's the fingerprint, that's the signature of molecular carbon dioxide. There it is, right there. Well, that wasn't hard. And then we took further observations with other modes of the observatory to get other elements. And what's been so wonderful with this telescope is that before we had to strain to maybe get one molecule, maybe, for some of these planets. Instead, we're getting a whole soup. We're getting water, carbon dioxide, sulfur dioxide. We're getting what's going on in there. What's the chemistry? What's happening? So we're able to understand what is going on inside these planets. What are they like? And that's something we've never been able to do before.
And I mean, planets that are so far away, right? Like these are hundreds of light years away.
Some of them are really close, just a couple light years away.
Wow, that is incredible. So, you know, we've talked about massive planets right now, but as an Earthling, you know, can Webb study, you know, small rocky planets like that as well?
It can, and actually there is a very well-known system, which is a TRAPPIST system, and that has 7 planets within the Mercury orbit for you to, so it's a lot of, you have the star and 7 planets packed into that very small orbit. So with Webb, we're studying them all. So far, we have results for the 2 ones closest to the stars. And the results have been, well, they don't have an atmosphere. We have been able to measure the temperature of one of them. And there is a lot of effort going on the characterization of the rest of the planets. So what everybody wants to find, I think, in this case for the rocky exoplanet is, can we find one that has an atmosphere? So it's all about pushing the boundaries and getting more and more data to get high quality results.
So Maka, could you, I guess, help us understand what all this means in the big scheme of things, right? So
so in the 90s, we didn't know about other exoplanets. Now we know about that. I mean, we have found about 5,000 of them. So it's all about pushing the boundaries of our knowledge on how our exoplanets form, what types are there, how are their atmospheres, like how the atmospheres evolve and change with time. It's all about putting in context the planetary formation and then really perfect our models and keep on observing. I mean, I see often this astronomy and science in general, like you're putting pieces of the puzzle together to get a really good view of the whole picture. So that's what we're doing.
I mean, and that's beautiful. So thank you both so much for such a great introduction to Webb's last year in science. And we are already getting so many great questions in online that I'm going to take a step back and I'm going to toss it to our viewers. So for those watching, remember to send in your questions using the hashtag AskNASA or drop them directly into the comment stream wherever you're watching. Alrighty, so our first question is from Instagram user Trevor Maria. So he has a question about the anniversary image. He asks, this is a multi-photo stacked on top of each other of different wavelengths of what each camera sees, correct? This isn't what it looks like to the naked eye, basically, is what,
Yeah. Can I take that one?
Sure, go ahead.
So
we like that
let
one.
me break down, let me demystify this.
Okay.
There's really not pulling a fast one here. So this is all one camera. This is the near cam instrument. And with that camera, we do 2 colors of light at once. We get a twofer. Buy one, get one free, which is useful. And so, but when you get the raw data, and you can download the raw data from the telescope. You can go look this up for yourself. The raw data are gray, right, where it's more light, less light. It's monochrome. But you can look at the raw data, and it looks a lot like this. What we do to make these really gorgeous images is we give the data a spa treatment, right? I mean, we make them look their best, we clean them up, but they still look like themselves. We're not doing anything to really change what's going on here. We just kind of make it pop.
Yeah.
And so what
Add some blush.
Yeah, exactly. There's a little bit of like, but there's nothing, you can look at the raw data and see everything that you see in this image. What we basically do is assign colors that our eyes can see to different colors of light that Webb is detecting. And so we try to do that in ways that make physical sense. So in this case, we've assigned the yellow color to dust, to emission from smoke, from little pieces of smoke. And so then we're assigning red to molecular hydrogen. And so we can be flexible, because of course we can't see the infrared, but there's nothing magical about our eyeballs, right? My cat can see further in the red than I can, and bees can see further in the blue than we can. Telescopes allow us to see past the limitations of our own eyes, and then we map them into what we can see so that we can make sense of it, because we go through life in color, and so that, astronomers do that. When we're analyzing images, we make 3-color images so we can help see, okay, what am I looking at here? What's going on?
Wow, I mean, that is just incredible. And it really, I feel like, brings out that merger of art and science in a way.
It definitely does.
And so that's so cool. So on our next Twitter user asks, Reg Victors, he's asking a question. If the Webb telescope can look with such detail at the very farthest reaches of the universe, can it see with extreme detail what is in our own Milky Way galaxy? Basically, if it can look so far away, does that mean if it looks a little bit closer, can it see with really, really great detail? And he has an example. Can it catalog solar systems and the detailed compositions of the bodies orbiting them?
Yes. To answer the question, yes, certainly we can study, and we are studying our own galaxy. And actually, this image was released today is from our own galaxy. It's a really close star-forming region. So yes, we are studying planetary systems like TRAPPIST. I mean, they are really far away. So what we see with these planets is maybe if you see the planet, you see a dot. You don't see, these beautiful renditions that are more like art than anything else. But yes, we study them. We do direct imaging. We do a rainbow with the data, and with that rainbow we get all the chemical composition and we can characterize them. So far we are studying for outer solar systems, let's say, or solar exoplanet systems, the planets themselves. We haven't started yet doing any sort of other body there, but yes, we can certainly and are studying our own galaxy.
Well, I mean, that just leaves us excited for what's to come, right? You know, it's only the first year. So Astroza on YouTube asks, will JWST try to find distant quasars?
Ooh, yeah. Yeah, we've already found a bunch.
Yes.
In the first year, we targeted some quasars we already knew about that were discovered by other telescopes. And there have been recent results out studying those quasars, and in particular wanting to understand, so these are supermassive black holes. A quasar is a name for a black hole with the mass of up to 1 billion, with a B, solar masses worth of stuff in a black hole that's about the size of our solar system.
Wow.
That's at the heart of a galaxy. Every galaxy has a supermassive black hole in its center. Big galaxies have big black holes. Small galaxies have small black holes. We don't really quite know
Quasar
why.
a supermassive black hole?
A quasar is a good question. A quasar is a supermassive black hole that is feeding, that is accreting gas down onto it. Right? Yeah, and so it's fueling. It's getting bigger.
Yeah.
And of course, once matter falls into a black hole, it can never escape. So none of that light gets back out. But as gas is falling down into the black hole, it's colliding with other gas, and it glows white hot and into the ultraviolet, and even you get X-rays, and it can outshine the host galaxy, and that's what we call a quasar. So in the first year, Webb has been studying some of the galaxies that host those quasars to understand, how did they grow so fast? How did they build 1 billion solar masses in 1 billion years down in the center? Webb has also been discovering supermassive black holes, accreting black holes that we didn't know about, that are just popping up all over some of these deep fields where we stare at a blank field, we find thousands of galaxies, and some of those you're like, oh, that's a quasar. There's another quasar. They've been popping up all over.
There are a lot.
And why are we so interested in studying them? Quasars or black holes?
It's all part of the galaxy evolution picture. It's all part of the puzzle. So actually, you remember me with the quasars, often you do have to remove the quasar to be able to see the galaxy underneath, and there are techniques to do that. But it's all about studying the galaxies and how they are formed and evolve.
Well, we have another question from a Twitter user. Radio Casterful asks, could JWST take a picture of Voyager 1, or is it too small to pick up on camera?
Oh, that's a good question. All right, do math on the fly. It's too small.
It's too small.
It's
I don't
too
think
small.
yeah.
Yeah, you can't do it.
But I love the question.
Yeah,
Yeah, I know. That was an insightful question. Thank you.
I'd have to actually do the math to work out whether you can get the reflection even if you can't resolve it. And I can't do that in my head. I'd have to go get a pencil.
Yeah, phone a friend.
Yep.
Well, we have Maddie Lane on Twitter who asks, what temperature does Webb operate in deep space?
Well, we have two ranges of temperature. So we have 3 instruments that operate in the near infrared, and they are at about 40 K, which is like a few tenths of degrees over the absolute zero. And then we have MIRI that operates on the mid-infrared, which means that you have to be colder to be able to detect that signal. So MIRI operates at about 7 K, which is just 7 degrees above the absolute zero. And that means that MIRI needs to have a special cooling system. It's like it has its own fridge, so to say, to keep it cool and really make it functioning. The other ones are cooled down by the sun shield that protects everything from the radiation of the sun.
Wow, the range is just...
It is.
Yeah. And then on the hot side,
the hot side,
right? The hot side where the below the telescope and the science instruments all really cold, minus 400 Fahrenheit, 40 degrees above absolute zero. On the hot side, it's like room temperature and hotter. So the parts that, like, where we keep the computers and the radio that phones home, all of that is nice and toasty. And then we have to keep that isolated from the cold side where we're doing the science.
It's like hundreds of degrees difference between the two sides. It's really a feat.
I mean, and it's just such a technological marvel, like no wonder it took 20,000 people to do this.
Really one of the hardest parts of designing and building Webb was separating those two temperature zones, very, quite hot and very, very cold, and having the hot not bleed down into the cold.
I mean, this is all so fascinating. And to those watching, thank you for such thoughtful questions. It really is a blast participating with you all in today's show. So please keep sending in your questions using the hashtag AskNASA or by dropping them directly into the comment box wherever you're watching today. We'll get to some more of those in just a few minutes. Now let's take a closer look at the planets in our own solar system. Webb has shown us clouds and storms on Uranus and Neptune, as well as their ring systems, which appear to be way more prominent in infrared light. Maka, what can we learn from an image like this of Neptune?
This is a beautiful image, and actually we have not seen Neptune, talking about Voyager. We didn't see these rings, many of these rings, since the Voyager flyby in about, I think it was 1989. So it's been many years.
Oh my
And
goodness.
so with Webb, we can really see in great detail all the rings. We can see 7 out of the 14 satellites around it, and we can see all these bright, shiny spots, and those are clouds in the atmosphere that are made out of a material, a type of gas that it's really reflective in the infrared, and that's how we see them that bright. So with Webb, we can see not only these details, but now there's more data, not only the first image. So astronomers are looking for more rings, the satellites we didn't see, and maybe even more satellites. So there's a lot of activity going on. And of course, at the core of it is like studying those atmospheres, those clouds, those storms. How do they move? What is the dynamic around the planet, and how do they evolve essentially year after year? So it's really, one could think, well, these are so close, why do you need such a powerful machine? And the answer is because we need all this detail. These are the closest planets to us, so it makes a lot of sense to study them in detail and then to think, well, how does this fit with the exoplanets we talked about before?
And I can only imagine that, the more detail we get, that must inform missions and things like that as well, right?
Oh, absolutely.
Exactly.
Absolutely, yes.
And in part, as Maka said, the last time we got an image of Neptune that crisp, we had to send a probe all the way to Neptune.
Yeah.
Here, we're just, the Webb telescope is not that far from the Earth. It's just pointed out there and seeing, so it lets us look at the outer solar system without having to actually go there. And it also is informing things like places where there is activity in the outer solar system, like Enceladus, the moon of Saturn, where we're following up on discoveries made by NASA's mission Cassini, which is now over with. But now we can go back and look and see, okay, what was going on that Cassini saw and follow up on it. So that's something I think is one of the neatest discoveries so far.
It really is.
Has been the water plumes coming out of the moon Enceladus, and how there's this plume of water that is escaping out of cracks in the icy crust from what is presumably a subsurface ocean down there. And we're seeing that escaped water. And so Webb has captured that and has taken spectra, little rainbows, to see what it's made of. And so that was something where we didn't have that instrumentation on board Cassini, but we could do it now after the fact. And we can visit all of the outer planets and the comets, asteroids, Kuiper belt objects without having to send a probe.
That is incredible. And so I do actually, what you said just reminded me, we had a few questions back we asked, I think, about Webb's temperature in deep space. Webb is not in deep space, is it?
So Webb is about a million miles away from
You
the
would
Earth.
consider it is? Okay.
Yeah,
It is pretty far away. Yeah.
It's 4 times past the distance of the moon. It's further than humans have ever gone.
Exactly.
Yeah.
Right, but compared to the distance of even Jupiter, it's not that far. So, we say hi to it, and it's like less than a light second. It's not that far away.
That is true.
In the
Actually,
big scheme at the
But
end.
it's not like Hubble, which, when Hubble is at its closest approach, it's only 300 miles over your head, right? So
Yeah.
in that sense, it's a million miles away.
Yeah.
So, if we're going to talk about ringed planets, we got to talk about Saturn.
Yes, we gotta
Webb
talk about
has
Saturn.
released an incredible image of this planet. And so, other than just sheer beauty, what can we learn from this image?
Sure. You want to take that one?
Sure. I mean, yeah. So again, the solar system experts, they call Webb a ring machine because they are seeing the rings of all these planets in such a
ring
detail. And this,
machine, I love
it's
that.
like a ring machine. And so these rings are made out of dust and ices, and that is where, with infrared and with Webb, you can really see the details and you can really understand. Are there, what are the satellites in the rings? What is the composition and their dynamics? And are there more rings we don't see? For instance, Enceladus is like a little bit farther away in a ring that is not the typical ring you see in the images from Saturn. So again, lots of data, lots of new information. And really, it's a fun fact is that the planets, they are so bright that the challenge with Webb is not to get too bright and then make the data difficult to observe. So the challenge is really get good quality data in a really, really short time. And that's what we're doing.
Well, I mean, it seems like it's knocking it out of the park. And so before we move on from solar system, I do want to ask, you know, Jane, is there any other object in the solar system or anything else Webb has been doing in the past year?
Oh, gosh, we've been doing a lot. And I don't have time to talk about all the comets and asteroids we've been studying. I do want to mention one asteroid that we observed when it was hit by another NASA mission, the DART mission, which on purpose slammed into one of a pair of asteroids that were orbiting each other in order to measure, can we move an asteroid if we needed to do that to protect our own planet. And so that was something that was a real stretch for our team. Webb was not built to track an asteroid that's moving that fast. That was 3 times past our speed limit. But there's a lot of cool science that we could do if we can track objects moving that fast. And so our team was really pretty eager for that challenge and embraced it. And in fact, we captured the plume of junk coming out of that asteroid as it was hit by the DART probe. So that's pretty neat, technically. It also lets us study, okay, what's going on in there, and are they rubble piles? What is the composition of these? So we did spectra. We took rainbows to see what the stuff was that was coming off this asteroid. But I'm proud of the team because I know how hard we worked to get that to work, because that thing was zooming past, and we're like, you know, having to move our telescope pretty fast.
And thanks to that, now we can move the telescope faster than we thought about before launch. So we can do science of faster objects.
That's incredible. Like that. I mean, like, talk about an all-star year for this telescope. So it really is amazing to see what it's been accomplishing. And there are so many questions coming in online, so let's get to a few of them. As a reminder to those tuning in live, you can submit questions using the hashtag AskNASA or drop them into the comment stream wherever you're watching the show. We'd also love to know, what has been your favorite Webb image from the past year? Post it online along with your question using the hashtag AskNASA. All right, our next question. Actually, this is a collective question. So we have a few viewers on Twitter who want to know more about the anniversary image. So they're asking, is what we're seeing in this image in the past?
Yes. Yes, it is in the past.
Can you explain how that's possible?
It is 390 light years away in the past, because that is the time the light takes to travel to us. So it is in the past, and actually everything you see is in the past. When you look at yourself in a mirror, you're looking at a version of yourself that is like a tiny fraction of a second slightly younger than you are at that moment. So yeah, it's light travel, and of course the universe also expands. So depending on where you are, it might take a bit longer. But yes, everything we look with Webb is older. Yeah, it's just
we're
the
always
nature.
Looking into the past.
We're looking, but it's like the light from the sun is slightly into the past. We are looking at each other slightly into the past.
It's mind-boggling, you know, to really like sit and think about that. And so, actually, this is a great follow-up question. Adam Updike on YouTube asks, has JWST changed our perception of the universe? And if so, how?
You know, not yet. Yeah, I'm going to go for not yet on that one. I mean, yes and no, right? Like, it's gorgeous, it's lovely, but we kind of knew that. We were going like, this is going to knock people's socks off, right? And remember having to reassure reporters before launch about, well, are the images going to be as good as Hubble's? So just wait.
Sit back.
No, don't worry. It's not going to be a problem. I would say that, you know, we are still getting started, and I would say that so far, for me anyway, what has given me confidence is that, you know, the data that we've gotten so far tells us, oh yeah, this is working great. This is, in fact, we can push harder than we thought. And so far, I think that we know that we can push quite a bit harder. I think maybe we'll get to it, but I think the high redshift, the very most distant galaxies, where we're looking back in time, not just 100 or 1,000 or a million years, but we're looking back in time 13 billion years. For me, that's probably the part where that's changed my perspective, just because for me and for everybody else before launch, that was a big old question mark. what did the first billion years of the universe's history look like? Nobody really knew. And that's the one area where we've gone from saying, well, we just can't do that with any telescope we have. We just hit a cliff where it's like, we can't see that far back in time to where, oh yeah, we're finding hundreds of these galaxies everywhere we look. And that's the part where we've gone from saying, how did it all get started? How did the first galaxies form? From, oh, we don't know, to, okay, now we have lots of data and we're really starting to figure out how quickly galaxies got their act together.
I feel like, that only probably opens up more questions, right? So,
But I think it's giving us new information in every area and really informing everything.
so I have a great follow-up to that. Webb is, again, knocking it out the park. And so we have a few people asking, what was the original life expectancy for Webb?
Yes.
And has it changed after this first year?
So, can I take that? Yeah. So before launch, the life expectancy, so the requirement was 5 years. Before launch, with the fuel on board, et cetera, we thought it would be 10 years. During launch, the launch was so optimized and so well done that we did save a lot of fuel. So now, if we think, we have to think about the limiting life factor, essentially. If you think fuel, then it will last 20 years or more. But we don't know exactly what will be the limit and how everything will evolve. You want to follow up?
That's perfect.
So fingers crossed. So that it is the 20 years. So we have another collective. Several users on YouTube are asking if Webb has found life on other planets. Now, from what I understand, this is not a life-seeking mission, but that Webb looks for biosignatures. Could you tell us more about that?
So the answer is no.
The answer is no.
We have not found life on other planets.
Yes.
We'll let you know if that happens.
Yes.
Nor was Webb designed to do that.
Yeah.
That is a job for a future telescope. And in fact, we are working on that. There's a design, we're starting to design something called the Habitable Worlds Observatory, which would do exactly that. Uses a lot of the same technology as Webb. It looks, it has hexagons, it deploys, but it looks at the same light that we do, visible, and then ultraviolet light. Webb can't do that. It's an infrared telescope. There's just some basic limitations. We're not going to find life.
And it's not looking for signs of life.
No,
right?
that is not our science case. What we could do is find places with Webb. We may be able, if they're out there and they're close, to find planets that could be habitable, that look nice and toasty, but not too hot, that have liquid water. But what Webb cannot do is say, yep, that one has life on it. That is a job for a future mission.
They can say, this looks like a nice destination that life might want to vacation at.
To study in the future.
Yes, and so, okay, thank you for that. Okay, so we just asked viewers to share their favorite image in the chat, and now Chalkstar on Twitter wants to know, oh, this is a good one. After a year, what is your favorite image from JWST?
I must say, I'm going to go with today's image.
Oh,
really?
Before that, it was the Stefan's Quintet with MIDI. But I have to say, the image from today, it is mind-blowing to me.
It's like ethereal.
It is, exactly.
Wow.
It's organic and ethereal. It's like beautiful. And the one before was the Stefan's Quintet with MIDI.
I wouldn't have guessed that. Okay. I'm going to go with Pandora's cluster. Which is a galaxy cluster, so thousands of galaxies all crammed into a space that in our neck of the woods is just a couple galaxies. So that's probably my favorite. The other one I really love is SMACS 0723, which is the lensing cluster that we revealed a year ago. Just because for that one, it was so beautiful. And it's also the science that I do, so I was like, ooh, this is exciting. And it was also really easy. We got those data, the telescope started observing around midnight, and we had the data by breakfast. It was just one of these like, oh, okay, it's working really well. So that one has a special place for me just because it was a demonstration to the world of how transformative this telescope is.
Wow.
If I may add, the Stefan's Quintet, just to add context, is the image where you have a group of galaxies that are interacting, and you really see how they they have like this cosmic dance, and they sort of distort each other, and in that process, you know, they may form a new galaxy. Definitely, they may form new stars. So it is beautiful.
I mean, thank you both too. And I know that y'all look at these images all the time. And so like, it really is incredible to hear which ones are y'all's favorite. So our next question comes from Mr. Spaquito on Twitter. I know that's a
Like it.
That's a good one.
That's a good handle.
How much time do the teams at SDSCI and NASA take to publish Webb's data? So starting from observing from the telescope and then going through the whole process of analyzing and rendering them out and then publishing.
So
What's the timeline?
So the timeline, it depends, right? So first of all, STSCI and NASA's institutions don't publish data. Like there are scientists that do publish data, but the way it goes, you take the data and then it gets downlinked. We have downlinks twice a day. So it gets downloaded essentially. And then it goes through what we call a calibration pipeline, which is what Jane was describing before. You know, get rid of your electronic effects and the things you don't want from the data. And that is automatic, and that is done at STSCI. And then once that process is finished, then it goes into the archive. And then the investigator team grabs the data, and they may say, oh, I'm going to fine-tune this, I'm going to fine-tune that, and then they have to analyze it and do their science. So it can be any time from, I've seen papers coming out in literally 2 days, and others take maybe 6 months.
6 months, a
A
year.
year, it really
how-
depends.
yeah.
Wow. Well, thank you both so much for these answers to these questions. For those watching at home, we'll get back to some more questions in just a few minutes, so keep sending them in. So we've now looked at our own solar system, right? Let's go back in time to when the first galaxies were forming. Webb is a powerful time machine with infrared vision that is peering back over 13.5 billion years and is already providing the first look at the earliest galaxies that formed hundreds of millions of years after the Big Bang. So again, we're hearing a lot about Webb being a time machine of sorts. Maka, could you explain how telescopes can even be time machines?
Yes, and this is nicely linked with the question we had before about in the past. So light is a wave, and it travels. So we know it takes time to travel, and it travels at the speed of light. So when the first galaxies and stars, they emitted their light 13.5 or more billion years ago, that light started to travel in time and space. And it did travel in a universe that is just expanding. And in that expansion, that wave gets stretched. And in that stretching, it moves, for instance, from the visible light to the infrared light. It gets redder. And that's where Webb can catch it. It's really a beautiful process. So we are looking at a time of the universe we have never looked at before. With Hubble, we looked until about 13 and a little bit billion years ago. There were other missions that looked even behind that, like WMAP and COBE. But that time where the first galaxies and stars were formed, it's really new, and it's really what we're looking at. We're literally looking at the edge of what Hubble did and really pushing forward the limits. So it's that's how it is a time machine.
It's mind-blowing.
It is mind-blowing.
It's honestly mind-blowing. And so, you know, Jane, but how can we really know how far away any given galaxy is with so much accuracy?
Sure, it's so convenient that, so we take rainbows is the short answer, and very conveniently, there are little markers, little diagnostic kind of like, if you think about like CSI forensics, there's little fingerprints of what different elements and molecules are that just stand out. And you can say, oh, that's oxygen, that's carbon, that's hydrogen. And anywhere it is in the universe, you get these little spectral signatures in the rainbow. And you say, well, that's hydrogen, there we go. And so it's really helpful that those signatures are there in galaxies. But as Maka said, because the light has been red shifted because of the expansion of the universe, all we need to do is say, oh, there's hydrogen. I measure what color I see it at. I know what color it was originally. That means I know how much the universe has been stretched as that light was traveling to us. So it lets us take what we measure, which is a redshift, and then we use a cosmological model to turn that into a distance. So what it basically means is we get little rainbows of all our galaxies. We then can figure out distances to every one of their galaxies. And so if you think of like take a deep field, like the famous Hubble Deep Field, where we've got hundreds of galaxies all peppered over an image, getting these little redshifts means that we can make that into a 3D, right? It's not a flat image
like
anymore.
pane.
We can do, we know the panes, right? We can say, okay, this galaxy is these are the ones, these far away, and we can start making a 3D model of where everything is. That means we can start saying, well, okay, these galaxies we're seeing as they looked 13 billion years ago. These galaxies are as they looked 13.4 billion years ago. And these galaxies are 10 billion years ago. And so for any galaxy we look at, we get a snapshot. We don't live long enough to see galaxies evolve. We just don't live long enough. But we can, by getting all these snapshots, put together that picture of how galaxies evolve with time. It's as though we never got to see humans age, but we got snapshots of people at different stages of their lives, and from that we can piece together how people are born,
I love
mature, and get old.
Yes.
That is a great analogy. So, what is Webb revealing now that we could have never known a year ago, right?
Can I do that one?
Sure, go ahead, yes.
So the big result, so there are a lot of results for the early universe. They're coming out fast and furious.
Yes.
So the ones that I think that sort of, to kind of group them into some big themes.
Yeah.
So far we're learning that there are more galaxies at early times in the very young universe than we expected. That's cool. They're also brighter than we expected, so they're easier to study. Great. There's lots of them. What we think is going on, and we're getting spectra of them, and we're finding, so what we're finding is that galaxies formed earlier than we thought, and they are forming more stars than we kind of gave them credit for or thought we might optimistically get.
Yeah.
We didn't really know. Honestly, we had huge uncertainties in what we might get in this first billion years. This really was well, that's why we built the telescope, was to go find out. But the main result that is emerging is that there are more of these galaxies. They're brighter than we expected. My interpretation of that is that galaxies just got organized early. And we're still working out why and what the details. They just, exactly.
They got cities.
So these are all still very small galaxies compared to the Milky Way, both in terms of size and in terms of mass. But they have a lot of the properties of bigger, later galaxies. They've made some I'm kind of proud of them. They've gotten their act together. They've formed black holes in their centers. They're accreting gas. They're forming stars. So that's a little, okay, these processes that we see in the nearby universe are working in that first billion years. And so we're understanding how we're really getting a gorgeous view of how galaxies turned on and got organized in the very early universe, which was the science case that sold the telescope. That's why we built it.
And interestingly, some of them, we know now that they have stopped star formation.
Or
very
pause,
early.
they're taking
They
a break.
have paused, they're taking a break. And maybe some of them will start merging with their neighbors and really triggering star formation again. So,
or maybe their black hole did it. We
maybe
don't know
the black
yet.
hole did it. We don't know.
But
And
that's a neat result. Yeah.
Exactly, and that is how galaxies will evolve until today.
Wow. So let's get to some more questions from our viewers.
Sweet.
But first, we want to know, where have you seen Webb images over the past year? With the mission's incredible window into the universe, I mean, we have seen pictures on clothing, billboards, in Times Square. Where have you seen Webb? Drop your response into the stream wherever you're watching. All right, so now on to some next questions. We have some Facebook users who are asking more about how we apply colors to the black and white photos that we get from Webb. Could you go into a little bit more detail?
Yep, I can take that. So as Jane was explaining before, every instrument has a camera. We call them detectors, but it's like a camera, talking about images. And what the cameras detect, they do detect photons, they detect light. And in this case, we use filters to select which part of the infrared light. Think if it was visible, you would use a blue filter and then you would get all the blue photons. It's similar. You use a filter in the infrared that you get those specific photons. So you take maybe 3, 4, 5 different filters. And then you order them chromatically. So your blue filters, you assign them the blue color on the visible. For the redder filters, you assign the red color, and then in between. So that's what the imaging experts call chromatic order. So they assign to each infrared color that we cannot see, a color that we can see. And it's literally just one by one, and then they combine them. And in that process of combination is that space where you mentioned before that there's also art in this.
Yeah.
Because, you know, they really do this fine tuning of, oh, let's optimize this, what is more pleasing to the eye, and they come up with this really beautifully, highly contrasted images. But each of the colors, it's real, and each of the colors represents something. One will represent dust, the other molecular hydrogen, the other oxygen. So it is in there, and it really gives a scientific meaning to the image.
I mean, you know the phrase like a photo is worth 1,000 words or something. Webb is really doing this right now,
is
right?
really,
Like not
yes.
only is it beautiful, you're just learning so much about the universe and just the connection of everything. So thank you for that wonderful description. We have another great handle. Tofu Eating Cat on Twitter asks, a great question. Are there any opportunities for citizen community science with Webb data?
Sure, that's a good question.
Yes.
So first I should say what citizen science is. That is efforts that are efforts to get real interesting investigations that are done by large groups of people in the community who are not trained scientists. And there have been wonderful examples of this in all fields of science, ornithology, in astronomy. And so for Webb, we are still actually working on figuring out how we want to, what our strategy for that should be. All of the data go public. Some of them have a 1-year period where they're secret except to the team that proposed that data. But after that year, they all go public. So we have a rich archive that anyone can access.
Yes.
And it really is fun to just start zooming around and start playing with the data yourself. You don't need to be an expert to start wrestling with and making the same face that astronomers make, which is the confused, you know, the face as we're dealing with the real data. So that's the short. So we're working on it.
Yeah.
And if you have ideas, let us know, because that's something to for the future.
Yeah, thank you. And so for those actually interested in citizen science at NASA, you can visit citizenscience.nasa.gov and explore some of our projects there as well, while we keep our fingers crossed for maybe one in the future with Webb one day. So we have Twitter user Christine Kuga, who asks, just how deep in the universe can Webb see as opposed to Hubble? So I guess, can we get a little comparison on their distances? Maka?
Yeah, I mean, Hubble was what, 13.23 billion years ago? And Webb is going 13.5 and beyond. So it's, what it feels like a small window when you think of the number, but it's really huge in terms of evolution of the universe and in terms of what happened there.
Because that first billion years, a lot was
A
going
lot did
on.
happen. From,
Getting organized.
getting organized, exactly. Get all your stars together.
One of the results that's been so gratifying for me has been to see that with Hubble, we really could just look at the colors and say, well, that's the right color red to be one of those very distant galaxies.
Because it's visible light,
well,
right? Or
and just we couldn't take spectra. We couldn't get the rainbows. You could just get the colors and a couple filters. With Webb, we can get beautiful rainbows. And in fact, we can get rainbows for dozens of galaxies at the same time, because the NIRSpec instrument has this neat multiplexing, where I want that one, that one, that one, that one, that one, all at the same time. And so with Webb, we're not only saying, yep, I know exactly how far away each of these galaxies is, but I know what they're made of, right? There's the hydrogen, there's my oxygen. Why is there so much nitrogen in that one? Which has been a puzzle in some of these, right? We're getting both very familiar diagnostics and some that we're like, oh, I've not seen that before. What's different about these early galaxies compared to galaxies in the universe today?
So really good follow-up to that. Twitter user Aerospatial is asking if Webb needs to take a pause after each image. Essentially, is it true that Webb is always observing, always operating 24/7?
It is always operating. I mean, you take an image, you take a pause, say, to switch your filter or switch your selection of your rainbow, and then take another image. And then you finish to take data for your, say, raw Fuki. And then the telescope has to move to the next target. So while it moves, typically it wouldn't get data from the sky, but it can get some calibration data, and then it goes to the next target. So it is essentially observing all the time, except when we do particular, like uploading a new software or taking specific engineering data for, processing and understanding how things are going. But yeah, it is, I wouldn't say 24/7, there are little pauses in between, and then you have to get there to your target. But usually when you go to a region of the sky, you optimize it and you do all the targets that are planned for that particular region.
It's safe to say it's working overtime.
Yeah, well,
It is, yeah. It's just constantly taking data.
and every week we give it a new plan for the next week. We schedule a week out, and twice a day we say hi and download all the data that it's taken in the last half of a day.
And even when it downloads data, it keeps observing.
Keeps going,
So
right?
it's very,
Yeah.
very efficient.
The telescope that could, So we are running out of time, but I do have one final question. What's next? What's next for Webb?
Sure. So we are exactly 1 year into our science mission. We have selected the science for year 2. That science just started. We started observing that July 1st. And right now we're doing a mix of finishing the targets that we hadn't gotten to yet from the first year and starting the targets from the second year. And we'll do a mix of that. The first year will ramp down as the second year ramps up. We're about to ask the world, all right, y'all, what are your best ideas for year 3? We're going to ask that for a deadline in the fall. And we're really just keeping it coming. And I think that one of the things I'm really gratified to see is that the easy stuff came out in the first couple months, and now we're starting to see the papers that really took some analysis with the harder analysis, which gets to the more interesting results. So I think our big results are still ahead of us.
That is so exciting to think about, too. And thank you so much, Dr. Rigby, Dr. Marin, for taking us through this journey of Webb's first year of science. I mean, I think it's safe to say that the best is even yet to come. So we really appreciate having you here today.
Thank you so much. Really a pleasure being here and sharing this celebration with everyone. Yes, it's been fantastic.
And thank you, and thanks to folks who've been with us on that journey. And stay with us. There's more to come.
Yep. And thank you to everyone tuning in online. I mean, I love that we were able to answer so many questions, and we really hope that you'll keep following the mission as Webb continues to peel back the curtain to the mysteries of the cosmos. To stay updated, follow NASA Webb on Facebook, Twitter, and Instagram. You can download the highest resolution images, videos, and other assets at webbtelescope.org. Now, remember, and I cannot stress this enough, this is just the beginning. Webb's first year of science is an amazing start to what this observatory will continue to do as it transforms our understanding of the universe. To go more in depth on the mission, visit web.nasa.gov and make sure to follow along as Webb continues to unfold the universe. Thank you, and see you next time.